Okay, so this video is on exponential and logarithmic functions. So the three problems that I have here are fairly standard. So we'll just go through them. So number one says, suppose that you want $6,000 at the end of a 4-year investment where the annual interest rate is 3% and is compounded quarterly. How much must you invest in order for this to happen? So what we talked about in class, there's this formula that we have, and we have that the future investment B is equal to the principal times 1 plus the annual interest rate divided by however many times you're compounding in the year, k, all to the power of k times t, where t is the number of years where this is happening. Okay, so in our case, here the b is the 6,000, that's how much we want. What we don't know is the p. We want to know how much do we have to invest in order for this to happen. The r we know is 3%, right? So we're going to write that as 0.03. The k is 4 because it's saying we want to compound quarterly. And the t is also 4 because we want to invest within 4 years. So let's get rid of this stuff. So we have all the information except for p. Okay, so we're just plugging all of that stuff in. So we have 6,000 equals p times 1 plus 0.03 divided by 4. I want you to be very careful. Remember, you have to put your percentage as a decimal in this formula or else it will not work. Okay, and then we've got 4 times 4. So we've got, simplifying a little bit, 6,000 is equal to p times 1.0075 to the power of 16. So we can solve for p by dividing. So we got 6,000 divided by 1.0075 to the power of 16. And if you crunch that into a calculator, you'll get something close to $5,323.91. Okay, so that's how much you would need to invest in order for you to be able to get $6,000 at the end of 4 years. Okay, for the next question, something similar, but different than what we've seen before. So a company promises all investors that if they provide $5,000 now, in 10 years they will have tripled their original investment of $5,000 through continuous compounding interest. What annual interest rate must the company use to make sure this happens? Right, so we've pretty much solved for every variable except for the interest rate. So I thought this would be a good opportunity to do that. Okay, so first thing we want to know is that the continuous compounding formula is the future investment equals the principal times e to the power of the investment, the annual investment, annual interest rate times time, t. Okay, so, well, first we know that we have that p is 5,000, right? And then b is triple the principal, right? So it's times 3, which is 15,000, right? So we have, so for $5,000 to triple, that's 15,000. So, and what was the other part that we have? And it's over 10 years. So we also know that t is equal to 10. So we've got everything we need except for r. So if we plug everything in, we've got 15,000 equals 5,000 times e to the r times 10. Okay, so just simplifying a little bit, we end up getting that e to the 10r is equal to 15,000 divided by 5,000. Right, so all I'm doing here is just dividing by 5,000. then in the next bit, we know, okay, so then e to the 10r must be equal to 3. And to get that r out of there, remember we have to take the ln of both sides. So we do ln e to the 10r equals ln of 3. So remember, whatever you do to one side, you have to do to the other. So if we're taking the ln to get the r down, we have to do ln on the 3 to make sure equality holds. Okay, so then we use the properties of the ln where we're able to rip out the exponent, and then it just leaves us with ln of e, and then you've got ln of 3. So the thing that we know from class, right, is that ln of e is equal to 1. So what we're left with is 10r is equal to the ln of 3, and then you can use your calculator to figure out an approximation. So r is equal to the ln of 3 divided by 10, which is approximately equal to 0.109. So to throw that in percentage, right, so therefore it's 10.9% is needed. As an annual interest rate in order for that to happen. Okay, so the last problem here is also something that we haven't really done, but we're definitely capable of doing it. So what we're asked here is, suppose the size of a population P, given in millions, over t years can be determined by the function P of t is equal to 60 times e to the 0.3 t. At what rate is the population size changing during the third year? So whenever we hear the word rate in calculus, that means take the derivative, right? So first thing we need is the derivative. And then once we have it, all we have to do is plug in 3. So p prime, so we're taking the derivative of this thing with respect to t. So this is d by dt of 60 e to the 0.3 t. By the constant multiple rule, we can pull the 60 out, and this is just the derivative of e to the 0.3 t. And then we know from doing tons of these examples that what we're going to get from that is 60 times 0.3 e to the 0.3 t once you take that derivative. Okay, so then simplifying that just a little bit, this is 18 e to the 0.3 t. Okay, so that's the derivative. So the derivative is 18 times e to the 0.3 t. And we want to know what's the rate when t is equal to 3. So p prime of 3 is equal to 18 e to the 0.3 times 3, which is 18 e to the 0.9, and that's approximately positive 44.27, right? So how do we interpret this? Right, so remember that the population size is in millions and time is in years. So if we're changing, or so the rate of change here, so therefore the population, first of all, is increasing because the derivative here is positive, right? So the population is increasing at a rate of 44.27 million people per year during the third year. Okay, so I just wanted to kind of show you that, like, you know, all this derivative stuff that we've been doing throughout the whole course, it applies to this stuff and it's used all of the time in real world scenarios. So yeah, I just thought it'd just be interesting to show you, and it's a very good application of exponentials and population modeling and that kind of stuff. So that does it for the video on exponential functions and logarithms.